Good morning. I'm T. Omiobidi. In this lecture, we want to present a practical representation of forces in equilibrium. Forces in equilibrium exist in just about every aspect in nature. In construction sites, it's so readily obvious there, in moving equipment, and in anatomical features. One of the examples we will see is one where we apply the forces in equilibrium to a person reading, or we look at the forces at play, the equilibrium forces at play for a person in reading. So this has a wide application. But let us start with an example of a situation in a construction site. What you see happening here is a crane, a boom on a crane, and it's, of course, lifting different loads that would be impractical for human beings to carry, or that might be difficult without this kind of device. And what we will do is we will look at an example of this device and use that to look at the forces at play in equilibrium. Remember the picture that we have here. We're going to have a representation of it. Now, this is more or less what you just saw earlier on. So let's look at a situation like this where we have a boom. This is the boom. This is the tractor that's holding it. So we have the crane set up. So let us look at a design that mimics the video that we just looked at. We have a 14-meter boom as shown below. It has a mass of 1,000 kilograms, and if it lifts a 3,000 kilogram mass, this is a mass that this boom is going to be lifting. So if it lifts a 3,000 kilogram mass to the position where we have it right now, what we're required to do is find the tension T in the cable and the reaction at A. This is A. We want to find the reaction at A. The tension in the cable, T, and the reaction at A. Those are the two things that we are required to find. Well, how do we set this up? Let us look at the setup for this. Well, this is a setup that represents the diagram that we just looked at. We represent the forces present. This is the mass that has been pulled down, 3,000 kilograms. The acceleration due to gravity, weight is mass times the acceleration due to gravity, mg. So this is our mg. So that gives us this value, 29,430 newtons. So we have that for the weight that's been pulled up. This is an equilibrium situation. There's no motion. There's no dynamics involved here. So we are able to use the laws of equilibrium to find the forces in that either movement is going on at a constant speed or it's at rest, Newton's first law. So this is the weight. Now the tension in this cable can be broken into the X and the Y component. So this is the T that's acting. And so we can break that into its X and Y component. When we break that T into its X and Y components, we have T sub X right there, and we have T sub Y. So that force has been dissipated into its two components, to say two-dimensional representation. And we're already given that the tension, the cable is acting at an angle of 15 degrees from the boom. So we have that. Now, when we add that 15 degrees to this 45 degrees, we'll have a total of 60 degrees. So we know that the boom, the cable is acting at 60 degrees to the vertical. We have that information. Well, so we have a total of 60 degrees from the cable to the vertical position. Now, the first thing we want to do is find the dimensions in each of these areas, because the goal is, again, remember, there are two things we're looking for: the tension in the cable and the reaction at A. Those are the two things we're looking for. We know that sum of forces in the X direction is 0, sum of forces in the Y direction is 0, and the moment about a given point is 0. Now, in this arrangement, the first thing we want to do is determine this line of action of the tension in the cable. We'll go on and we'll find the tension first, and after we get the tension, we'll find the reaction at A. So let's proceed to get the tension. There are different ways you can go about it, but probably a simple way is to go on and look at this scenario that we have, this T, and use the information that this T, we know we know the orientation to the x-axis, and we know the orientation to the y-axis. We already found out that this is 60 degrees. So if it's 60 degrees to the y-axis, then the y component, T sub y, is just going to be T cosine 60 degrees, and T sub x is going to be T sine 60 degrees. So we also know that the boom, the weight of the boom is acting at its center, the center of mass of the boom. So this is known because we know the entire length. That means this is 14, this entire length is 14 meters. From here to here is necessarily going to be 7 meters. It's halfway. So with that information, we re-represent that here. We re-represent this here. For this is primarily for the geometry, whereas this is for the forces in play. So let's clean this up and focus on the geometry now. Let us look. So let's take care of the geometry. We find the length of AE and the length of BE. AE is BE only because this is 45 degrees. If it was a different angle, we would look for the different lengths. So we know AE is BE is 14 cosine 45 degrees. We do the same thing with AD. This is AD. AD is half. It's just going to be half of this. This is going to be half of this entire length from the arrangement that we have. So we know the length of AD. We also know that this is actually some necessary bookkeeping. We know TY because T has its component in the X and Y direction. TY is just T cosine 60 degrees, and TX is T sine 60 degrees. With that set in place, let us proceed to take moment about point A. Let us take moment about this point. So it's to remember the the arrangement, the design that we have, this is the hinge. This is where the forces F, Y, and Fx are acting from. So we'll take the moment about point A. When we resolve all the moments about that, we've defined a direction, counterclockwise positive, clockwise would be negative. So summation of moment about A is 0 for equilibrium. So you sum all that, take the moment of all the forces acting, and take the total moment about A. We would get this expression, which finally gives us T equals, in this, we have 93,811.48 Newton meters. So that's our T. We have T value, 93. So we got T. Now that we have T, we can go on and find the reaction at A. Go back to this expression, and we now have a value for T. If we then use another principle of equilibrium, summation of forces, you can do summation of forces in the Y direction or summation of forces in the X direction. Either of them would work. I've done both, and I just put this in parentheses. It's actually the summation of forces in the Y direction that has been used to get this answer, but it doesn't matter. That's just an option for you. But then go on and sum the forces, and when we sum the forces in the Y direction, summation of forces in the Y direction is 0. So we look at these forces, this 46,905.74 newtons. That's our T sub Y. That is this one. Okay, that's actually this one that's represented here. That's the T sub Y. And then we have also the weight that's been lifted. That's 29,430, and that's right there. And then the weight of the boom itself, which is 9,810, which is that. So all those are forces coming down, and F sub AY is the force going up. We balance the forces, set their sum to 0. That gives us the value for F sub AY. Remember, we want F. We want the force acting here in the boom. We want that force that's acting at that point. So that force is given as F sub AY sine F sub AY over sine 45 degrees, and that gives us the reaction at the boom. So that's how we do that, and we get the forces that are explained in each case. We will now look at another example of the representation of these forces. Well, actually, the ideal way to get this done is find the forces in the Y direction and the forces in the X direction, and have Y over X, and that should give us about 46 degrees, which is a little more than this one. What I've done is an approximate value here, and because the positioning in this particular design is such that the resultant force, which ideally is something like this, is acting very close to this. We do an approximation there. This is an application as it might be used in the construction industry or in design. There's intelligent approximations made, and that will be one of them. And so we have the value, the approximate value for F sub Y, 121,828 newtons. And that is how that is done. This is another example. Construction worker. There's a lot of engineering mechanics involved in civil engineering, so expectedly there are applications, especially in the construction industry, but it's certainly not limited to that. Let's look at this one. We have a construction worker shown below. He pulls a rope AB. He pulls this rope AB to be able to raise the joist BC. To raise it, over to a position where it is right now. Now the question is how much tension is in this rope? How much tension is in this rope T, and what is the reaction at the step right here? How much tension is in the rope, and what is the reaction at this step right here? Well, when you look at this, there are three bodies acting. So this is a three-body diagram. So the approach that we will use to solve this is a three-body diagram approach. Again, this is a representation of the occurrence, what is happening at the construction site. We represent the three-force member as shown below. This is a joist right here, and this is a string, the rope that's pulling it. This is the rope that's pulling it that the guy was pulling from here, and this is the weight of the boom. So we have three forces. So this is a three-force member. And remember, three-force member, well, one is a rigid body with no force couples, is subjected to three forces, or forces that are reducible to three forces. And those forces are either acting concurrent or they are all parallel. In this case, we have a case of the forces acting concurrently. There's this weight acting straight, there's this tension, and necessarily the reaction has to pass through that point of the intersection of the tension and the weight. So this is a three-force member, and we will use the three-force member property to solve this problem. Okay, let us proceed. What we have is, again, we draw the joist, and let's see if I can make it bigger a little bit. Okay. So we quick description. Okay, good. We have this scenario. We draw the joist, and we consider these distances. We already established that it's a three-force member arrangement. So we draw the joist, and we want to let's remember the things that we're looking for. We are looking for the reaction here and the line of action of that reaction. That's right here. We're looking for that. We're also looking for the tension in the rope. That's T right here. So those are the two things. To proceed, the first thing we probably want to do is find this angle. The reason we want to find this angle, either this angle or this angle, and well, we know this angle is it's 60 degrees. We know this angle is 60 degrees. So how do we find it? We're already given that the tension, the rope is acting at 30 degrees to the joist, and we know the joist is at 30 degrees to the vertical because we're given that it's at 60 degrees to the vertical right here. So we have enough information to determine that. And once we determine that, we will find ultimately this height, this little height. Why is that important? Well, if we can subtract this height from this, if we can subtract this height from the entire height, we will essentially have found the value here, the value of this height here, because it is the same as this, okay? This 2I equals. So we find this. We look for this height. By finding this height, once we get that, we're able to get this value. Once we have that value, then we have a useful tool to be able to determine the angle theta that we're looking for. So let us proceed and do that. CK is that entire distance. It's 5 the length of the boom of the joist is 5 meters. So CK is 5 cosine 60 degrees. We find BK. BK is from here to here. It's 5 sine 50 degrees. Then we find ED. ED is this distance. ED is necessarily half the length of the joist because it's acting through this. It's the length of the joist. It's uniform. Because it's uniform, we know its mass is acting through its center of mass. So we use that information to determine that ED, which will be the same thing as FK, which is actually the same thing as CK. Because this is the mass of the joist in its position and the weight is acting straight down at the center of gravity, we know that this distance is equal to this distance, okay? And it's equal to this distance. So these three are equal. Just find one of them, and we have the others. So, and that is half CK. This, again, this entire distance is CK. This is half of it, and we look for that. That's 1.25 meters. So we get those. Why is this useful? Well, the next thing we want to do is find BD. We know that BD over ED, BD right here over ED is tangent of this angle, and this angle is 30 degrees. So we go on and we find BD. Once we get BD right here is ED times 30 degrees, it gives us the value for BD, which is shown in a small separate diagram here. Now, we can go on and subtract the value of BD from BK. Do we know the value for BK? Sure we do. The entire length is 5 meters. BK is 5 sine 60 degrees, because this is 60 degrees. So BK is okay. BK is 5. You gotta pause it. Okay, we'll pick up where we left off. BK, which is here, is 5 sine 60 degrees, which is 4.33. Now, 4.33, that gives us the value for BK. We already just found the value for BD, which is right here. So just take BD from BK, we will get this height. That's what we're looking for. That height, which is the same as EF. Okay, EF is the same as DK. This is DK, and it's equal to EF, which is this, from here to here. So the height is what we just found, and we find it to be 3.61 meters. Now, so what it means is we now know this. And we already know this. Now, this over this is tangent of the angle that we're looking for. So we say EF over CF, EF over CF is tangent theta, the angle we're looking for. And that gives us the value for theta, which is 70.9 degrees. So the reaction at the location here is happening at an angle of 70.9 degrees. What is the value? What is the value of that R itself? Well, we can use the sine law. Application of the sine law would give us the value itself. We already know we already know where it's happening, where it is acting from. It's at 30 degrees to the horizontal. That gives us this value, and this represents the weight of the joist. So if we take this from 90 degrees, we will have this angle, and we already know that this angle is 30 degrees. The angle sum in the triangle is 180 degrees. That gives us the value of this angle, which is 130.9 degrees. So we have all those. We have all the angles, and we have a weight value already. That gives us enough information using the sine rule to find T, that's the tension in the rope, and R, the reaction at A. And in this case, we get T is 96.3 newtons, and R is 222.45 newtons at 70.5 degrees to the horizontal. And that's how we do that. As you can see, these are everyday things in construction sites and other places that the principles of engineering are used, and equilibrium is applied to be able to make a determination of the force that is at play and the force that's of interest. Given one force, we can find the other using these laws of equilibrium. We will look at one more example, then we'll make a general statement, and that should wrap it up for this session. The example that we will look at is one that has biomedical applications. All right, we'll see you then. Hello, welcome back. This is the last of the three examples that we want to present in the application of forces of equilibrium. And in this particular example has a biomedical application. Probably just about every student has experienced the things that we will discuss here. And hopefully it provides some insight and some idea to the student and on study posture to make studying a little more of an easier project or an easier task than it probably already is, holding our heads in a particular position for long hours. Well, in this problem we have the average weight of a human head is 5 kilograms. That's about the average weight, actually. I should say average mass, but we use the word mass and weight, knowing that when we go on to the application, we will have to convert the kilograms to newtons. So this is how it's taught. This is how the talk is done. You don't hear in public they say, "Oh, this man weighs 7,000 newtons." They go, "He weighs." They don't say he weighs 700 newtons. They go, "He weighs 70 kilograms." You know. So like we do it like it's done in street talk, but then we apply the engineering principles to be able to solve the problem. So we want to find the tension in the neck muscle, and for this student who is in this position, some information we're given. This is the neck muscle. The neck muscle will be some muscles that are packed here. And what happens actually is this neck muscle will be pulling to the muscle at the back because the head is bent like this, so that the head doesn't just drop. The neck muscle has to hold it in place. So there's tension here in the neck muscle. The tension there, and that tension is pulling at the back of the neck. And if the student is in this position for a long time, there will be pain in this area because of the extended stay in this particular position. So we see that this has practical application as the others that we've looked at. So this is the force that's supplied by the upper vertebrae that's just above the neck, or just in the muscles, in the front muscles. That is the force supplied by the upper vertebrae to hold this student in this posture. Well, in this position, the weight due to the head is coming down. So we have all these information here. So this is going to be 5 times 9.8 newtons, 0.81 newtons coming down, and this is the force that's provided 90 newtons is supplied by the upper vertebrae at 60 degrees to the horizontal. So this is 90 newtons is the force that the upper vertebrae supplies to hold this position at 60 degrees to the horizontal. So we have this information. Now we're looking for the tension. How much muscle pull is this guy getting? Poor guy. Once we know that, we can play with it a little more and maybe use it to make some other useful design. So let's proceed with that. This is the representation of what we just saw. We will. This is another approach to solve the same the problem. We could use another method like an earlier method that we used, but this is another variety, another approach. We have this representation, the tension that's pulling to the muscle, the back muscle that are tied to the bone. This is the tension pulling at the neck of this person. This is the force that's supplied by the upper vertebrae, and this is the head coming down. So that's our representation. We are already given the inclination of this force by upper vertebrae to the horizontal. So let's sum the forces in the y direction. If we sum all the forces in the y direction, we have the 5 kilogram, which is 5 times 9.81. That's the weight dropping down or tending to drop down. The y component of this 90 Newton force is just y sine 60 degrees. And the tension, this is alpha. We don't know alpha, we don't know t. So those are the things we're looking for. If we take this component of t, that would be t cosine alpha. Okay, so that's t cosine alpha, and that's what's represented there. So in equilibrium, because when you're studying, you hold your head in that position. The head doesn't dance around, so it's at rest in that position. It's maintained at rest by the force in the muscle, by the tension. You know, little headache may come along the way, but you keep that head in position so you can focus on the study. So it is an equilibrium situation, and this is the tension in there, and this is the y component of the tension. This would be the x component of the tension that's on the back of the neck. So we set up those forces. When we do that, we get the value for t cosine x, 28.89 newtons. We do the same thing for the, we find t cosine alpha is 28.89 newtons. We do the same thing for summation of forces in the x direction, and we find t sine alpha is this. Well, if we have t cosine alpha and t sine alpha, we can find the value of alpha, because all we have to do is find tan alpha, which is sine over cosine. It gives us alpha is 57.8 degrees. So we know that the muscle is holding at 57.3 degrees from the vertical position. That is from if the head was standing straight. So we have the value of that. And once we know that, we can go on and find the value of t. We know what t sine alpha is. We just found alpha, so we can find sine alpha. T sine alpha, we already know, again, from summation of forces in the y direction, we know that t sine alpha is 45 newtons. So we can find t, because now we know alpha. Put the value for sine alpha below there, and we find the value for t. T is 53.47 newtons that this student is applying to the muscles at the back. We can carry this much further. We can look at if we look at this situation, then the question can be, is there a better posture that the student can have? And yes, certainly there's a better posture that the student can have. The closer the head is angled to the back of the neck, that is the the smaller the angle between the positioning of the head and the vertical, which is alpha, the less the tension in the less the tension that the students will experience in the head. So these are different things that can be looked at and can be used in determining a proper ergonomic position in studies or in engineering or in other things that we do. All right. Thank you. That's it.